Hello, and welcome to our next lecture covering measuring extraction effectiveness. Today, we're going to be starting our last module for the class, talking about measurement and safety. By the end of this module, you should be able to answer the question, how do we know what happened to the molecules after extraction? And you should understand the safety of natural product extractions and concentrations. So today, like I said, we're doing measurements with our overarching question of how do we know what happened to the molecules? By the end of today, I would like you to be able to understand identification versus quantification, describe our major analytical tools, interpret things like a chromatogram, be able to understand, explain, and use calibration curves, calculate simple averages and standard deviations, evaluate extraction data quality, and compare extraction methods using this data. So let's start with a question. Let's say I have two bottles, bottle A and bottle B, that were made via two different methods of extracting from lavender leaves. Which one is better? Is it this one or this one? Think about it for a second. How can we judge these? Do we judge it based on the bottle? This one maybe looks nicer, but this one's darker. This one maybe has darker oil. This one has lighter oil. Fill level, how much we get, right? Well, let's think about these different possibilities, right? If we think about, something about the oil itself that we've extracted, you could say maybe this one has a darker color and this one has a lighter color. Does that mean that we ended up extracting more because it's got a darker color? Or is it possible that it's darker because there's impurities or oxidation? The lighter color, is it cleaner? Or maybe it's lower yield? Maybe it's pure. Maybe it has less depth, right? Maybe we're only pulling one thing out and we really want the whole range of different derivatives of the lavender, right? The issue is we just don't know by purely looking at it. We need a method to look at our molecular fates. Remember, we have talked about this over and over again, that we start with plant material, we extract some things, some compounds are altered, some are retained, some are lost. We need to know what happened. So in order to determine what happened, we generally are going to go through three overarching methods. So first, we want to know what exists in these bottles in the extract. We often want to know how much of it exists. And then we want to know if two or more products are the same or if they're different. And these are the sort of three topics that we'll cover today. First, I want to touch on what is the difference between identification and quantification. So identification is determining what exists. For example, in our uh, lavender extraction example, is this oil composed mostly of linalool or linoleal acetate, right? So is it, this one or both? And then once we know which of these exist, we often want to measure how much of each exists. So not just how much total, right, which we can do, but how much of each individual component, right? And so this is quantification. So how much exists. To do this, we use various analytical equipments to help us measure both what exists and how much of it exists. I'm going to go over some central key generally used pieces of analytical equipment. This is not to be an analytical chemistry class, but more just an overview so you feel comfortable with these terminologies, some of which we'll use, some of which we won't use. So the first type of equipment that's ubiquitously used in analyzing chemistry are spectrometry methods. So this includes IR or infrared spectrometry, visible light spectrometry, UV spectrometry, and optical emission spectrometry. These, in various different methods, are useful for identification and quantification. The second set is nuclear magnetic resonance. This is used for identification mostly, but can also, to some extent, be used for quantification. Chromatography is for both quantification and identification. Balances and scales are used for quantification, and things like a refractometer is usually used mostly for quantification. Over the next few slides, I'm going to take you through some of the key techniques within these different types of equipment, minus a balance or scale, as I figure you are familiar with concepts of weighing things. Okay, let's start with spectrometry because this is one of the most widely used techniques. So in spectrometry, we usually have some sort of light source, and that light source has light, and it goes through what's called a collimator, which reflects the light down, collates the light, which then is sent through a prism or grating. And that prism or grating, shown here, separates the white light into its various wavelengths. A wavelength selector selects one and only one wavelength of light, which is shown, which is passed through a sample solution held in what's called a cuvette before it's going through a detector. So we end up having a single wavelength of light, ideally, go through our sample, and then we measure how much light has gone through. And so this is the fundamental idea in spectrometry. Let's start with IR spectra, or infrared spectrometry. If we look at the various length scales of the electromagnetic spectrum, so light, IR sits right here, so just below visible light. And so it's going to have wavelengths which are longer than what your eye can see. What happens when in this spectrometer is we pass light through the cuvette and we see how much has been absorbed, or rather, how much has not gone through, right? I know how much light I send into the cuvette. I measure how much comes out. So anything that doesn't come through, any amount that doesn't come through, has been absorbed. And we measure this absorption spectrum. So down at the bottom of this graph is the wave number. So this is the wave has to do with the length of the light, or which light energy is coming through. And then we get these on the y-axis, either transmission or absorption. And these are just inverses of each other. So we either get the points showing up or showing down, depending on how we're measuring. And what you'll see is in the case of hexanoic acid, we get these very distinct peaks, right? So, at 2,971 inverse centimeters, 1,700 inverse centimeters, etc. I don't, want to turn this into an organic chemistry class where we go through and really learn what each of these are. The more important thing for you to understand is, this chromatogram is a unique fingerprint, right? So if I, take a measurement in my cuvette and I see these peaks, all of these peaks here, and it matches, then I likely have hexanoic acid in my solution. Okay, if I have additional peaks, or I have peaks missing, right? So let's say this peak at 1,721 inverse centimeters, which is this CO double bond stretch. If that's not there, if I don't see this peak, then I don't have hexanoic acid in my solution. All right. So the other place that we look at is going just up the up the energy level of our electromagnetic wave. So this is called UV, or ultraviolet and visible spectroscopy, or spectra. So this is going to look sort of just like we had before. We're going to have wave numbers at the bottom, either absorbance or transmission on the y-axis, and we see these peaks. So here I'm showing examples of various uh, uh, natural product stats. So this is limonene. We've talked a lot about that. Eucalyptol from eucalyptus, eugenol, etc. Right? So hopefully these names are showing up. And what you'll notice is their structures, they have slightly different spectra, right? So this has a much lower peak than the limonene, and it's the limonene has this sort of hump at 240, where the eucalyptol does not. If we look at limonene versus eugenol, the eugenol has this peak around 280 versus the limonene does not. So right, we can start distinguishing these molecules one against each other, right? And even though the eugenol and the carvacorol look similar, if we go down, this shoulder sits close to 240 nanometers, whereas this shoulder sits much closer down to maybe 210, right? So I want you to think about these spectra as molecular fingerprints. Okay, so in both absorbance and transmittance, we shine light. The light goes through the cuvette. We measure the detection as a function of wavelength, shown at the bottom. We measure absorbance. A similar concept is fluorescence. Here, we take light, we shine it through our cuvette, but this time, instead of measuring what passes through, we measure what's emitted. And so here we have a light that goes through, and then for those who are really interested in chemistry, we have adsorption up, we have some sort of non-radiative transition, and then fluorescence back down between energy levels. And so this light that comes in for adsorption and the light that's given off for fluorescence are different wavelengths, so we can measure them separately. And because we're measuring the excitation, so that adsorption, separately from the fluorescence, we generally pull the fluorescence off to the side. And we can get a different fingerprint for fluorescence compared to absorption, because we're not only doing the excitation, so this movement of electrons from the ground state to the excited state, but we're also looking at this fluorescence as it's coming back down. And so this is often really useful for quantification, because if you looked at this previous slide, right, the limonene and the eugenol, if I have mixtures of these two sets, it can be hard to distinguish. But if I have a fluorescence, I have two knobs, right? I can tune in what knob I'm looking at for absorption and for fluorescence, right? And so I can tune this a little bit more and minimize overlap. And so we use this a lot for quantification. All right, so the last type of spectroscopy, major spectroscopy that I want to talk about is atomic emission spectroscopy. This is again going to be an emissive type set where we're going to excite the molecules. This is usually done with a flame, where we inject our sample, we pass it through fire of some sort, and then that fire causes excitations, and then we measure the light coming off those excitations. This can be shown, we can see this in a chromatogram. On the bottom, we have wavelength. On the x-axis, we have count, so measuring how much of each wavelength is detected. And we will end up with, once again, a distinct spectrum for each individual element. Because of this, this is really commonly used for detection of metals. So let's say you had a sample and you wanted to know if it was contaminated with something toxic like chromium or lead or cadmium or mercury. You could run your sample through an atomic emissions spectroscope and determine if those individual metals are present, and then if they are present, how much of each is present. All right, so we've talked a lot about how we can use this to quantify or to identify various molecules, but we can also use a lot of these spectroscopic techniques for quantification. And I want to start with an example of this. So let's say I take a purple molecule and I put a small amount of maybe purple dye in a beaker, right? Notice these beakers have the same amount of liquid in them. And I put a little bit of dye in versus a lot of dye, right? If I have a few molecules, the light that passes through barely doesn't interact strongly with the molecules. Therefore, my color is very light. However, if I have a lot of molecules, a lot of absorption is happening, my color gets dark. The actual spectrogram of these three beakers is the same, just the intensity of the color is different. Okay? Because of this, we can start measuring how many of a particular type of molecule exists because we can look at how much absorption there is. And we can do this using the Beer-Lambert law, or Beer's law, as it's generally shortened to. And Beer's law says that the absorption is equal to the electrochemical, the dielectric constant, absorption constant, times our concentration times the length. And really, what this means, don't worry about this, is this is a number is set for a specific molecule. Our cuvettes are always going to be a single size, so the absorption is directly proportional to the concentration of molecules. So how we use this is we pick a frequency of light, we measure absorption or fluorescence, whichever we want, and we measure a set number of standards, which we know the concentration of. And we measure their absorption and we generate a line. Okay? This is called a calibration chart, right? And so for almost all molecules across massive, massive, massive concentration ranges, we have this direct linear relationship between absorption or absorbance and the concentration. Okay? So we can make these calibration curves. We go into the lab, we take a standard sample, we measure that standard sample at different concentrations in our spectrometer. We measure them, we create this chart, and then we go in and we take the unknown sample. We see how much it absorbs. Maybe it absorbs at 0.06. I go over, I go down, and then we say that the concentration is, I don't know, 375 molar. And from that molar concentration, we can, of course, deduct quantities in a sample and yields. Okay. Next, I want to briefly talk about nuclear magnetic resonance. This is used for identification. The idea is when I put a molecule under extreme magnets, their behavior changes how light moves through. Light and magnets move through this molecule. I'm not going to go into detail. The key, though, is I get this spectrogram here. It's measured in ppm shifts, and each of these peaks corresponds to a unique hydrogen atom on this molecule. And so we can use this. This is very helpful in fingerprinting. It's very, very precise. Our last spectrometry technique is called mass spectrometry. What we do here is we take a small, very small amount of sample, we heat it up so that it vaporizes, and we take it down to a very low pressure and we sample it. The sample enters this mass spectrometer or mass spec. It's exposed to an electron beams, which ionize the molecule. And then those ionized molecules, so they're now either positively or negatively charged, move through a magnet. And those magnets, because charged species are influenced by magnets, they separate, and we can get the mass to charge ratio. These are measured on a detector over here. And so what we get with our mass spec is a relative intensity as a function of mass to charge ratio. When this molecule goes in through here, it breaks down. So we don't get just a single peak, but we get a variety of peaks that tell us what the mass to charge ratio is. And again, this is going to be unique for each molecule. Again, by measuring, if we know that limonene has a slightly different, has maybe 83, and linalool has a strong signal at 55, and they don't overlap. We could use those charge to mass to charge ratios to distinguish these in a flow and really measure them. All right, that's all of the spectrometry I wanted to talk to you about today. I want to briefly remind you about chromatography, because this is widely used in analytical techniques. Remember, we had previously used chromatography for separation. We're going to rely on that again. Here, remember, we take literally a column. So this is a tube of some sort. We fill it with some sort of media, and then we pour a carrier fluid through there. So the carrier fluid is moving through this column. We then put the sample in here. We continue to add additional fluid. The carrier fluid carries the sample through the column. Because of the difference in adsorptive preferences of the column between the two media, between the two species, we get separation as the material flows down through the column. We get the separation, and we can take aliquots and separate, the red component versus the blue component. This is the idea that we're going to use in analytical techniques as well. I'm going to start with gas chromatography, and we'll talk a little bit about that, and then we'll talk about other types of chromatography. So in this case, we have a gas flow regulator. So we're going to flow a gas through here. That gas is going to be our carrier fluid. This is usually done at relatively high temperatures. We inject a liquid sample, or if we have, we could inject a gas sample as well. The gas flows through here, and we end up passing whatever flows through this column out through a detector. And there's multiple different types of detectors. The key thing that I want to say is in all cases, the detector is really measuring differences of what's coming through the column. So it's measuring, say, differences in the character. So there's the gas regulator. This carrier gas is coming through. It's coming through. It's coming through. Oh, now there's something different coming through. That is recorded as a peak on this plot, which is shown as a function of time. Right. So first, maybe that blue or that red material comes through. It has a little peak. More time goes by, the blue compound comes through, it has a peak. Maybe there's a third compound that comes through at the end. Because of this, we end up seeing, here's a very low temperature, um, uh, low temperature configuration of our gas chromatograph. In this example, there's 1, 2, 3, 4, 5, 6 different molecules that this chromatogram has identified. If I run at a higher temperature, the peaks are going to come through faster, but they get crowded. So if we look down here at this higher temperature of the oven, we have 1, 2, 3, 4, 5 peaks, right? So we're missing that sixth peak. But in exchange for that, we get much shorter time frames. What's really happening is all of these peaks are getting squished, and you can see if I squish this one down, it might merge with this first peak as we go. Okay. So what we can do, and we're not going to do that in this class, but just so you're aware of a possibility, is you can program the temperature so it starts out at a low temperature to get good separation. And then as time goes by, we increase the temperature. And when we do this, we retain our 1, 2, 3, 4, 5, and 6 different molecules, and the time is significantly less than this low isotherm. Right, so there's all sorts of games you can play to pull these apart. And this includes not only things like changing the temperature, but also using different packing media in the column using different carrier gases. So we can do both identification and quantification in chromatography. In this case, we take a standard sample and we run the standard sample through our chromatograph at whatever conditions we want to run the detection at. So this would be, here's component A in the standard. We see it come through. We have component B standard sample. We see the time it comes through being run exactly the same program. Then we take our unknown sample, we run it through, and we see, some component A shows up, some component B shows up, and there's there's 4 other compounds which are showing up. This one, this one, this one, and this one. Notice how it doesn't tell us what these other 4 are, but it does very nicely tell us that component A is there and component B is there very cleanly. The additional benefit in chromatography is that we can do quantification at the same time. The concentration in the sample is equal to some sort of constant times the area under this curve, or how large this triangle is. So here's the sample over time. The detector picks up more and more and more and more and more, and then it starts picking up less and less and less and less and less, and then back to normal. So when I say the area under the curve, I mean the area of this triangle, right? So how much is here? Because the concentration is a linear relationship with the peak area, I can take this area under the curve, plot the area versus concentration in my standard, and then when I have my unknown sample, all I have to do is take the area under the curve, I go I go up to whatever the wherever the line is, and I can go and I can read off what the concentration was in my sample. Right, so we're very straightforward, easy, clean way to measure once I know what my materials, what's in my sample, or at least what I care about in my sample. Gas chromatography requires that these species are in the gas phase. So this requires our chromatogram to be running at, or chromatograph to be running at temperatures above our vapor pressure. If we run at temperatures below the boiling point of these materials, you can end up forming liquid plugs and wrecking your column. So therefore, things that really want to stay liquid, we shouldn't use gas chromatography for. Rather, we can use something called high performance liquid chromatography. This is going to be very similar to gas chromatography, but instead of having the sample flow through as a gas phase, it's going to flow through in the liquid phase. And our carrier is going to come, is going to also be a liquid. Right? So just like the gas chromatography, we inject our sample. Fluid is the mobile phase, that liquid is going to flow through. We end up getting this nice separation as it moves down through the column with time, and we end up getting signals that arise out of our detector. Again, it doesn't tell us what these species are, but it does tell us how much they are, and it performs very good separations. As before, depending on your chromatograph machine, you can have either one mobile phase or multiple mobile phases, in which case you can change, the temperature profile with time. You could change mixtures of different organics and aqueous solutions to really try to separate these materials as quickly and efficiently as possible. All right, so the last technique that I want to talk about is refractometry. In this case, we have a refractometer. This is a handheld one shown here. We have this sort of slip cover and the sample holder. We would put a drop of our solution on this this plate. We look up into light. That light comes through a prism into a light goes into this prism. So that's this piece right there, and where the sample sits on that edge side. Because that if you think about, like, say, a fish tank or a glass of water, when light goes through it, it changes angle. This measures the change of the angle, right? And so we can see this here. This was saying at 20 degrees C. If you were at 20 degrees C, the refractive index of whatever the sample is, I don't know, about 35, 35 of this unit, right? So again, you can look up the refractive index if you have a single component. Or if you have, the same component, you're looking at strength, you can make calibrations. Okay, so we've talked a lot about identification. We've touched on quantification. Just to reiterate this, through all of our different analytical techniques, what we do is we calibrate our instrument with known standards. So that means I very carefully measure out and say this. And I'm going to make some standards that have 1%, 5%, 10% of the compound I'm looking at. I construct a calibration curve. with the instrument under the exact same conditions that I'm going to run my sample through. I measure my unknown samples, and then I use my calibration curve to determine the quantities in that unknown sample. All right, now that we have a good idea of determining what we have and how much we have, I'd like to turn and say, how do we know if we're getting good results? Right, so if I do two different extractions, for example, are they the same or are they different? And before we get into this, I'd like to start with an example because I think this may help you visualize this. What happens if you flip a single coin? If I flip one coin one time, I might think that, hey, when I flip coins, I always get heads because when I flipped that coin that one time, it came up heads. But we know intrinsically that is not correct, right? I want to flip the coin multiple times to see what happens again and again and again. And only in doing so will I find that heads comes up 50% of the time and tails comes up 50% of the time. So let's say I take 100 coins and I flip them over and over and over and over again. Even if I flip one time 100 coins, I'm not guaranteed to get exactly 50 heads and 50 tails. If I flip coins to 10,000 times, if I flip 100 coins 10,000 times, and I count how many heads that I get in each of those times, what you'll see is this histogram, right? Where in general, we have about 50 heads, but it's not always 50 heads. We have this, what's called a normal curve or a normal distribution, right? And that's just due to randomness within the sample we're taking. Because of this, we can't just take one measurement and say that's that's what it is. We want to do things multiple times to see how consistent our results are. And we have names for that consistency and how to describe that data. So here we have that same distribution, right, that I showed over here, right? This is this normal distribution. I've redrawn it over here, maybe saying on the yield of extraction, maybe we've got, we did 5 extractive experiments and we measured yield at 8.6, 9.2, 8.9, 9.1, and 8.7. Right? This is just coming up because there's just natural variance within the herbs, within the instrumentation. So in general, we want to pull out two basic statistical pieces, one being the mean or the average, and this says where the center of my distribution is. Right? It's usually represented as this Greek letter mu. Right? So this says what is the mean, what is the average of all the samples that I've taken. We calculate that by summing up all of the measured points and dividing by the number of points we took. In this example, our mean is 8.9%. We also want to say how narrow this peak is, right? So the narrower the peak, right, that's saying that if I redo this experiment over and over again, I'm getting very consistent results. This is desirable. If I'm getting results that are, if instead of being, 8.6 to 9.2, if I was getting from 4 to 20, right, something is wrong with how I'm doing the experiment, right? So we like to see narrower standard deviation, narrower distributions. And we call this, we quantify this spread by the standard deviation. So how spread out that data is. And we call this sigma. Okay, so within one standard deviation, we expect about 70% of the data to be within one standard deviation of the mean. When we go out to two standard deviations, right, we add an additional 27%. So we're up to, say, 95-ish percent confident that our data should fall within two standard deviations of the mean. Right? And then we can do farther and farther out. The standard deviation is calculated as the sum of the difference between each data point and the average squared, divided by n over 1 with the square root. So in this example shown up here, the standard deviation is 0.24%. This is substantially smaller than the mean, which is indicating that our this data set is pretty consistent. We're getting pretty consistent results. We often want to indicate how confident we are in our measurements. So when we do measurements, we report two values, one being the mean that tells us what we think the average is, right, what I should expect to get, as well as a confidence value, right? So how, if I do the experiment over and over again, how confident I am in this mean. In this confidence value, there are several, about 4 different usual choices. The first being just the standard deviation. The second being some multiple of the standard deviation. So example, 2 standard deviations. So you would say, I measured this with a mean of 5 plus or minus 0.1, where this confidence value is measured as twice the standard deviation. We could also measure what's called standard error. So this is the standard deviation divided by the square root of the number of samples taken. Or we can use student's error. And this is a little bit more tricky. We take this standard error and we measure, we multiply it by this t-value. And this t-value enables us to not only say plus or minus that confidence value, but how, with what probability we're confident. So I'm going to talk to you a little bit more, but we'll come back to this table, this across the top. It's how confident we are, and these values that sit down here are the t-values, and then these degrees of freedom are 2 minus the number of sample points. Okay, so let's compare 2 yields. I have, once again, these 2 bottles. One has been made via, say, steam distillation. I've done steam distillation a few times. I get a average of a 75% plus or minus 3% yield, where that 3% is the standard deviation. When I do solvent extraction, I get 83% plus or minus 2% yield. So my question is the yield with steam distillation the same or different than the yield with solvent extraction? Well, if I look at this, you would say, well, 75 is definitely not 83. And it sort of feels like with these confidence intervals, there's not much overlap. So the steam distillation is probably giving us a much lower yield than the solvent extraction. Let's look at 2 other examples. Let's say I have one solvent, which is isopropanol, and one solvent, which is hexanol. When I do it with isopropanol, I have 83 plus or minus 2%. yield versus 85 plus or minus 3% yield. Are these the same or different? Well, 83 and 85 are not identically the same, but if I expect my sample to be, plus or minus 2%, so on the high side, right, that could be up to 85%. On the low side of 85% plus or minus 3, that's 82%, right? So we're seeing that these two yields, when I take into account the uncertainty, there's an overlap. So they're probably the same. But saying that these are probably different between steam and solvent extraction, and these are probably the same, isn't very rigorous, right? We would like to put a number. So we can actually compare two different yields. What we do is we go back to our T table, students' T distribution. And we do a few different calculations. First, we see what is the difference in the measured averages divided by this effective standard deviation. This standard deviation takes the standard deviation squared of each of our samples divided by the number of those samples and adds them together and then takes the square root. So that gives us S delta. We then can determine the number of degrees of freedom using this equation. This will give us the number of degrees of freedom. What we do then is once we have T and the number of degrees of freedom, I go down the number of degrees of freedom that this has told us. And then this across the top is the percentage. Here's my confidence interval down at the bottom. Sorry, this is what we want to use. The t-value at 80% confident, 90% confident, 95% confident, 98% confident, or 99% confident. Let's say the number of degrees of freedom is 3. I have a t-value of 2.5. If I want to be 90% certain that they're different, I would compare 2.3 to the 2.5 garnered for T. And we can say that T is larger than 2.3. So we would say, I'm 90% sure that these are different. We can't say that we're 95% sure that they're different, right? If we wanted to be 95% certain we were different, we'd have to go up here and look and see that I'd need a t-value of 3.18. And right, they get bigger the more confident you want to be. Okay, so there's there's sort of 3 different ways that we can increase our confidence. One, which you'll notice is, through changing the t-value. So the actual difference in the averages or the means causes t to go up. And the narrower the distribution is, and so the smaller the standard deviations are, causes S delta to decrease. That also causes t to go up. So the narrower the distribution is, the more certain you are in each sample, and the greater the differences between the sample, the higher the t is. Higher t, more certain they're different. The other thing that we can do is take more samples. That sort of shows up here. So as n increases, the number of degrees of freedom increase. This goes up, and you'll see that the t-values, as you have more and more samples, decreases. So you can be more and more certain if you have way more samples. So, right, if I have 30 samples, I have a t-value of 2.75. 5 and I'm 95% sure, versus needing a t-value of, let's see, sorry, 2.75. Only being, if I have only 10 samples, I can only be 98% sure, or only 95% sure if I only have 4 samples, or degrees of freedom, or only 90% sure if I only have 2, right? So you can see, there's sort of, more samples, narrower distributions, and larger differences will enhance our understanding that 2 samples are different. I want to quickly go through an example here. Let's say that we go back to our steam distillation versus solvent extraction example. Want to know, are these the same or the different? Let's assume we did 4 steam distillations, 4 solvent extractions. Let's see if they're the same or different. We start out by calculating S delta. We have a standard deviation of 3. I have 4 samples, so I put in 3 here, 4 here. In terms of solvent 2, we had a standard deviation of 2, once again 4 samples. When I plug this into this equation, I end up with 1.8. I can go over to t, right? T is x1 minus x2, so the absolute value of x1 minus x2, so 75 minus 83 over 1.8. This gives me a t-value of 4.44. So as soon as I'm seeing high t-values, this is starting to look like they should be different. We still, though, need to go down and look at our number of degrees of freedom. If I plug in the numbers into this equation, we should get 5.2 degrees of freedom. This is approximately equal to 5. I go to my chart. I see that 5 has a value of 2.015. We compare 4.44 to 2.015. We see that that is larger. Therefore, we're 95% sure that these are not the same. Okay? Let's do the same thing, but with the 2 different solvents. One which had 83 plus or minus 2% yield, and one that had 85 plus or minus 3% yield. In this case, our S delta is 1.8, but our averages are much closer together. So we have 85 minus 83, so our t-value is only 1.1. Much lower t-value. If we go across this chart, we can say at the 95% confidence level, the t-value is 2.015, which is larger than which is larger than the 1.1. Therefore, we cannot say they're the same. We could even go down to 90% and say, are they the same or different? And this is still, at 5 is 1.476, still larger, right? So we'd have to go down to a very, very low confidence level to say that they're different. And so in essence, these are statistically the same extraction yield. All right, so in summary of today, I want you to think about how we can do measurements and how they're going to flow. We start by looking at what exists, and then we generally want to characterize how much exists. And to do that, we need a calibration curve. And then once we have how much exists, we often want to find out, does it matter, or is it different or the same as other approaches, right? So with what, we do identification, how much is quantification, and does it matter is our statistical analyses. At this point, you should be familiar with how we can answer question of how do we know what happened to our various molecules. You should understand identification and quantification. You should be able to understand how major analytical tools work. You should be able to interpret a chromatogram, explain how calibrations work, how to calculate simple averages and standard deviations, evaluate extraction data quality, and compare extraction methods using data. All right, our last lecture we'll finish up next time. We'll be talking about how we can do all of these experiments safely. All right, have a great day.